Grade 12s, welcome to module number 28. I just had a look at what we're going to cover for this module, and it seems like we're getting a little trickier as the semester goes on. So hopefully you're still feeling like you've got lots of energy to go over a couple of topics. I'll try to make it as easy as I can. So here we go. There are two little parts to this module. The first one is looking at acids and bases and some terminology that goes along with those, something called a conjugate acid-base pair. It basically means the acid is named and what does it turn into, and the base is named and identified as a base, and then what does it turn into. Conjugate acid-base pairs is what we're going to go over first, and then the second part of this is looking at double displacement reactions involving acids and bases, and then there are some work through parts in the notes pages 29 to 32, 27 I have written down, I think it's 29 to 32. Also in the review package, you're going to go over questions 10 and 11, which is this part right here, and then questions 12 and 14 are the conjugate acid-base questions, and I'll go over a couple of those with you as well. Okay, so here we go. This isn't in the notes, and I think it was just made as basically a little aside. So just jot down the definition, and there are some textbook questions that go along with it in a couple of sections in textbook if you feel like you want to do some reading. 12.1, and that should be 12.3, I think, as well. Okay, so the concept of acids and bases is that you need to look at the definitions for them. We are using the Bronsted-Lowry acid to base definition, by which an acid is a proton donor and a base is a proton acceptor. Okay, think of it also in terms of capable of removing a proton. Basically, we're meaning a hydrogen ion, because it's those hydrogen ions that basically give us that definition of an acid and base, but it's not just hydrogen ions. Okay, so anything that donates a proton or anything that accepts a proton, that's the proper terminology for a Bronsted-Lowry acid or base. Okay, water can be acting like an acid or it can act like a base, so it depends on what it's with. Okay, that's an important concept, so we'll come back to that one. And then of course there's this idea of a conjugate acid-base pair. So let me just show you what that looks like, and then you can just kind of jot down this example here. So any reactant that acts as a Bronsted acid and donates a proton, because that's by definition what it is, it forms what we call a conjugate Bronsted base. It's like its partner. Here's an acid, it's a proton donor. What does it turn into? We call that its conjugate base. Look at which one is the base, which is going to be a proton acceptor, and then what does it turn into? That's its partner, and we call it a conjugate acid. Okay, so you can see right here that I've labeled them as their conjugate pairs. So you can see right here, here's my Bronsted acid, proton donor. What does it turn into? On the product side of our equilibrium, it's a conjugate base. Then you can see I've got my Bronsted base, because it's going to act like a proton acceptor. What does it turn into? It turns into its conjugate acid. Just see that? How the base turns into a conjugate acid, the acid turns into a conjugate base. Okay, and that's basically the definition of an acid-base conjugate pair. So in general, Bronsted acids and base reactions are equilibrium systems that involve two acid-base pairs, and so we call those the conjugate acid-base pair. I'll post my note on this one, even though I know it's in the solution set, but I wanted you to see that. Now, let's have a look at the review package questions that go along with this, because this is where you're going to pop in your definition. And I've already done, I've left this filled in from last semester, so I'll let you sort of use my note if you'd like to fill it in as well. You can see there that I kind of colored coded this. I had time to do that, so you can see we've got an acid, conjugate base, and I just labeled them 1,1 so you can see which pairing we've got, and then you've got your hydroxide going to the H2O, so a base and its conjugate acid. So you can see from the first example down below here, it wants you to just write what the equation is going to turn into, what does it make as a product, and then identify the conjugate acid base pairs. Okay, so here we go for the first one. HSO3 negative and CH3OO negative. Okay, let me just make it a little bit bigger for you here. What's that going to turn into? Okay, well, I know that I'm going to recognize it as an acid or a base based on what it looks like it's going to happen and what you know based on your names. You could just simply identify it. So that's your first challenge. Can you identify which one's the acid and which one is the base in this situation? Sometimes you don't know, and so you have to look at the table to see what's been given, and then you can tell if it's acting like an acid or a base. So it is a little bit tricky, okay? So for the first one, I know that it's likely going to go like this. With an SO3 2 negative, it's going to lose the hydrogen ion. That's what's going to act as my acid, okay? And I know that that acetate, the CH3COO negative, it is going to act like a base. How do I know that? Because I know that acetate likes to do that. So I'm going to pop it on there with the H, and now I've got acetic acid. But how do I label those as the acid-base conjugate pairs? Okay, so now I go back and I say which one acted like the acid? Well, I know it was the HSO3 negative. So HSO3 negative, okay? And it is my acid. What did it turn into on the product side? We call that its conjugate base, and it turned into SO3 2 negative. Can you see that? Those are the matching acid-base pairs, but it's the acid you're looking at is by definition the proton donor. And then what did it just turn into on the product side? So now you can see that what would be labeled as my base for the second one is going to be the CH3COO negative. It acts like a base. It's a proton acceptor. It turns into CH3COOH, and that's what we call our conjugate acid. So those guys are also conjugate acid-base pairs. Okay, that by definition is what it means to have a conjugate acid-base pair, and I'll leave it at that. Just work your way through. You can see that for this one down here, you needed to know this information, and same for the second one. It wants to show you that if you can't figure it out, what the water is going to look like, you'd have to be given some more information. So for the first one, it tells you that the H2O is going to be the proton acceptor. So it's acting like a base in the first example. But then look at the second example. Maybe water acts like an acid and is the proton donor. So sometimes you'd have to be given the information of what's the pH of a solution or how is it going to act. So that's interesting, isn't it, that water can act in two different ways. Okay, let's pause here, do those questions, and then part 2 of the lesson, we're going to skip all the way to the double displacement questions, and this one's really a self-working through section, again in the notes where you've got the answer given to you, so you can just simply put a piece of paper over top of the T-bar and then fill in the answers. Okay, I'll get you started and then I'll let you work away at it because I think you'll be able to figure it out. All right. Double displacement reactions involving acids and bases. We're looking at neutralizations here, okay? So acids and bases can be classified as strong or weak depending on their degree of dissociation in water. We know that a strong acid, you can still have a concentrated solution, and a weak acid can still be concentrated. So concentration is completely different from the definition of being strong or weak. Strong or weak depends on, does that acid dissociate 100%, or is it a weak acid or a weak base, and then it's typically a lot less than 100%. Somebody had asked me the question, are there anything sort of in between? Not really. They're either strong or weak, but within that weak range, you do have some degree of variability between the ones that are the weak ones. Some are weaker than others, but they're all in that category of weak as quite a bit less than 100%. Do you remember when we did our ionic equations and our net ionic equations back at the beginning of the unit? I want you to go back and have a look at that again if you need to refresh how you figure that one out, or sorry, how you draw your ionic and your net ionic equation, because that comes right into this lesson here. Okay, the first thing we would do if we were in class together is I would say, all right, find yourself a partner and I want you to come up with an acronym, and so you're going to be able to memorize the strong acids and the strong bases. If you can memorize the list of strong acids and the list of strong bases, then by definition and default, everything else is going to be a weak acid or a weak base. You need to be able to identify the strong acids and bases, because once you write your balanced chemical equation and then your ionic equation, if it's strong, you're going to write aqueous beside it as always, and then you're going to show 100% dissociation. If it's weak, you're going to write aqueous, and then when you do your ionic equation, you're going to keep it together because it mostly stays together. So that's going to affect your equations going forward. Okay, so memorize the strongs, and then by default, everything else is weak. The strong base list is pretty easy, actually, so start with that one if you'd like. Okay, once you've got your strongs memorized, then you're going to look at the equation, and you're going to be able to now identify these as strong or weak, and then look at the salts that get formed, because again, these are double displacement reactions we're looking at, mixing acids and bases together. You're going to look at the salt that gets produced, and then based on what we did earlier in one of the previous modules, you're going to recognize that as one that has good solubility or poor solubility, right? Those ones that are slightly soluble. Do you see where we're going with this? You're going to put all your information together now and, and see if you can actually write these equations based on what you know, okay? This is where, at the beginning when you started to do chemistry in grade 10 and 11, you're like, how does anybody figure out what the products are when you've got a chemical reaction? Well, now you know more information, so you're a lot smarter than you were before, so you can actually figure that out. I'll get you started. Okay, so here we go. For the first one, you can see how it's all set up here. And it says, write the balanced chemical, ionic, and net ionic equation for the reaction between hydrochloric acid and sodium hydroxide. Okay, so what do you do first? You're like, all right, I've got hydrochloric acid. That's easy. I know how to write that one down. Sodium hydroxide, I know how to write that one down. Are they strong or weak? Based on what you've just learned, you're going to identify these as a strong acid. And what about sodium hydroxide? Strong base. Okay, acid plus a base gives you a salt plus water. So now when you do your ionic equation, when you recognize this as a strong acid, you show it as being strong with 100% dissociation. So you write your hydrogen ions and your chloride ions, right? Then you take your strong base. You're like, well, strong base means 100% dissociation. So you write your ionic ratio that you've got, 1 sodium ion to 1 hydroxide. Okay? Then you can also look at your salt, but that one's super easy. You certainly know that's good solubility, but of course you would do that again and you would write out your sodium ions and your chloride ions. See how it goes? And then remember, for this section, you've got now the answer down below, okay? So you do a sample question, write the answer down. So these notes work really well if you don't have a printer to print your notes, right? You can just do a couple of examples. And you bet that every example is going to be given a different version of this. So we're going to look at strong acids and bases, strong acid, weak base, strong acid, weak base. So there's probably 4 examples, yeah? Okay, recognize that. Write them down as those different examples. So let's look at the next one. Oh, here's our strong acid, strong base example one more time. Sulfuric acid, strong acid. Potassium hydroxide, strong base. Okay, so when you write out your ionic equation, I write my strong acid as such. I write my strong base as such. Okay, and then I look at my product that I get, and we know that potassium sulfate also has good solubility, so my good solubility is shown with my ions dissociated down there. Okay, let's go on to the next one. Next example, acetic acid and sodium hydroxide. Okay, acetic acid, weak acid. Sodium hydroxide, strong base. So write your balanced chemical equation, write your ionic equation, recognizing the fact that you've got a weak acid. So let's see in the answer if that's there. There you can see the answer to that. Weak acid. So what do you do in your ionic equation? You write it as a weak acid because it's going to be stuck together and not dissociated 100%. Okay? There you've got your strong base with good dissociation because it's strong. That's by definition what it means. And then you've got your salt that you make, sodium acetate, good solubility, 100% good solubility. So that's how you know what you're going to write in your ionic equation. Okay, that one's pretty easy. I'll let you work away through that. I just highlighted these ones so you can kind of get a sense of where we're going. Okay, hydrochloric acid, strong acid. Magnesium hydroxide is the salt that gets formed, and if somebody in the question tells you it's a solid, then you believe them and you write it as a solid, meaning there's a precipitate, poor solubility because it is insoluble, makes a precipitate, keep it together in your ionic equation as a solid. Okay, next one. Hydrofluoric acid and ammonia. Weak acid, weak base, because they're not on your list of memorized strong acids and strong bases. Okay, a little bit of extra information coming down below, and then this part of the next question gives us that information again that we memorized, I think from the first module in this unit, where you looked at the unstable compounds that decompose to form the gas. Okay, next question, hydrochloric acid, sodium carbonate, strong acid, soluble, therefore you know what to do when you write your ionic equation for that one. Okay, barium hydroxide, ammonium chloride, we've got a strong base, and ammonium chloride is soluble, so then again you're going to follow that through. Okay, so you're going to go all the way to the bottom of page 32 with all of those different examples, lots of practice for you, and then when you get to the review package, you can also do questions 12 to 14. And it just summarizes nicely, actually, your list of strong acids and bases and what those look like when we show them as equilibriums, when we show them as going to completion. And then what would the Ka value be if you were to calculate those numbers? That's sort of where we're headed in the next module anyway. Okay, so good luck with that. I know that was a bit tricky, but good luck, and we'll talk to you next time.